Okay, with that in mind, I'd like to get into what's going to be the last topic we're going to cover this semester, which is one that, again, I find the students, but I've taught 373 a lot of times so far, and, basically at this point in the semester, students are usually beaten down by the life of the semester. NP-Complete, graph algorithms is hard, dynamic programming is hard, everybody's tired. NP-Completeness, which is what we're going to talk about now, is something that is an idea that I get the sense students like. They don't completely understand it, especially at first, and it looks kind of amazing. But NP-Completeness is an idea that is almost a philosophical or a religious kind of an idea. Okay, it's going to tell you something about how the world works and how the world is organized. More than just being kind of a hacker technique or a algorithm design technique. NP-Completeness is about an idea. And, again, once you see it at first, it's going to look like a strange idea. But once you get to understand it, there's something kind of exciting going on. And so I'd like to introduce the idea of NP-Completeness sort of at first by a puzzle of what you would like to be able to do. Suppose all of you guys are hoping to get a job after this. Okay? Your boss may give you an assignment. It says, we need an efficient algorithm for the Bandersnatch problem. And they send you off to go write up or find an algorithm. And what happens is you fail. You're trying to find a fast algorithm and you can't find a fast algorithm. What should you tell your boss? Now, one possibility is you didn't find a fast algorithm because you are too dumb. Okay? This is a bad thing to say to your boss. Why is it bad to say to your boss, I couldn't find an algorithm because I was too dumb? Because the boss may think about hiring someone who's smarter than you. So everybody get that idea. So you don't want to be able to say that. You would like to be able to say, ideally, I couldn't find an algorithm, a fast algorithm for a problem, because there is no possible fast algorithm for it. If the boss had sent you to the work, he said, I want you to give me a linear time algorithm for sorting using comparisons. You could go back to your office and then say, I can't figure it out, but wait, Skeena showed me in here something about decision trees, and there was, he proved that there was no possible fast algorithm, no possible algorithm better than n log n for that. Okay? It would be great in your predicament if you couldn't find a fast algorithm, if you could find a lower bound proof. The reason I could not find a fast algorithm is because, there is no fast algorithm. That's really what a lower bound proof would show. Now, the trouble with this is that except for basically the sorting algorithm, there is not the sorting lower bound. There is really not a single algorithm lower bound that I think is interesting in general use that I stumble across, okay, except for the sorting lower bound, okay? So in general, unless the boss asks you that one problem or something very, very close to it, it's probable you can't give a lower bound, saying, damn it, there is no fast algorithm for it, okay? What the theory of NP-Completeness lets you answer something that's almost as good, which is that you can look at your algorithm problem and rigorously say, boss, I can't solve it, but nobody else in the world can solve it. You don't believe me? Skeena couldn't solve it. Joe Mitchell couldn't solve it, okay? Don Knuth at Stanford couldn't solve it. I can prove to you that no one in the world can solve this problem, okay? And that's the kind of a guarantee that kind of NP-completeness is really on some level fundamentally offering you. You can take problems and prove that, okay, you can't absolutely sworn in blood prove that there is no possible fast algorithm. But the amazing thing is you can prove that nobody in the world knows how to do this problem. Okay? And that is, in my mind, almost as good as it. Okay? People are pretty good at algorithm designing. I'm pretty good at algorithm designing, right? You can prove that I can't do it, okay? It's not quite the same as saying it can't be done. That would be very arrogant. But saying that no one in the world can do it, that's a pretty strong guarantee. And that's the kind of thing that you're going to be getting from an NP-completeness reduction. Any question? And this is kind of a hard thing, because how would you normally think you would prove? How would you go about proving that no one in the world knows how to do something? Okay? There's one technique that would seem like an obvious technique for doing that. What would that be? One possibility is ask every person in the world, right? Do you know how to solve it? Do you know how to solve it? But that doesn't seem like a very practical thing to do, right? But the NP-completeness proof is going to get doing. And if you think about it, proving that something doesn't exist is a hard thing, okay, or a strange thing. Who here believes that unicorns exist? Okay, do we have any unicorn believers here? I don't see any unicorn believers, okay? How would you prove that if a unicorn existed, how would you prove it? That's actually pretty easily. You'd go bring me one saying, clunk, here's a unicorn, look at it, okay? If unicorns did exist, it would be easy to prove that they exist. How do you prove that a unicorn does not exist? Well, this seems like a harder thing, right? You got to look everywhere. You know, inside that door, you see that door? Do you know where that door goes? How do you know there's not a unicorn there unless you look at it, okay? So proving something doesn't exist is a different kettle of fish than proving something does exist. That's what I want to kind of clarify. And the theory of NP-completeness gives you a way to prove that essentially things don't exist by proving that nobody believes that they exist. Okay? Any questions? And in fact, it's not just a popularity thing. There's actually a deeper lines of reasoning, but we'll explore them as we go. So what does the theory of NP-completeness have to deal with? Several times in this class, we have talked about problems for which we could not find an efficient algorithm. First day of class, I told you about this robot, this robot tour optimization problem. That in fact is the same as the famous traveling salesman problem, which is given a set of points, find the shortest path, find the shortest tour that visits all of those points exactly once. Okay? Okay? I don't know a fast algorithm for the traveling salesman problem. I don't know a fast algorithm for a lot of different problems. Okay? And, you know, but we also can't prove somehow that there is explicitly, that there's no possible shortest path algorithm for that. What the theory of NP-completeness does is it sort of gives you a way to show that all the problems we don't know how to solve quickly are really the same problem. This is kind of why we're going to ask everybody. I'll know that no one in the world can solve this problem. If I can show that there is one problem that everybody agrees that that we don't know how to solve fast, and if I can show that your problem is really that one problem, then everybody agrees you can't solve your problem fast. The theory of NP-completeness is that all problems that we don't know how to solve are somehow deep down really the same problem. Okay? Any questions about that? This is still generality in philosophy and things like that. But any questions about that? Okay. What do I want to now say? The theory, the real idea of what NP-Completeness is about is on this slide and the next slide. If you understand this slide and the next slide, you will understand everything I'm going to do for the next 2 weeks. And I'll show these 2 slides at the beginning of every class for the next 2 weeks to make sure that you see it again. And so what is the idea? Suppose I give you an algorithm, the following algorithm, to solve the Bandersnatch problem. What is the Bandersnatch problem? Bandersnatch is the name of a problem. Maybe it's traveling salesman, maybe it's shortest path, maybe it's sorting, maybe it's some algorithm problem, right? If it's an algorithm problem, it can be solved by an algorithm. And what is this algorithm to solve Bandersnatch? Bandersnatch problem takes as input a G. Maybe it's a graph problem, maybe it's not, it's just the input we're calling G. The way the Bandersnatch problem algorithm works is it converts G into an input instance for the Bobilli problem. What is Bobilli? It's some kind of an algorithm problem. We talked about minimum spanning tree, we talked about all pair shortest path, we talked about, it's an algorithm problem. Okay? And suppose that our algorithm works like this. We translate the input of the Bandersnatch problem. We reformat it so it's an input to the Bobilli problem. If we now have the input to a Bobilli problem, we can call a Bobilli solver on this translated input. Right? So we can call a Bobilli subroutine on this translated input y, and we will get an answer. Okay? What kind of answer do we get? Well, it depends upon the Bobilli problem, of course. Right? But what if this Bandersnatch algorithm works by whenever we call Bandersnatch of G, we instead return the answer of Bobilli of y. Y is the translated input. Okay? And if it's correct algorithm, then the answer to Bobilli of y has to always be equal to Bandersnatch of G. Okay? I want to compute Bandersnatch of G. How is this algorithm doing it? It's doing it by reformatting the input and calling a Bobilli subroutine. Okay? If we did that translation in a seemingly magical way, such that Bobilli of y is always equal to Bandersnatch of G, then this is a correct algorithm. Does everybody see that? If Bobilli of y is always the same as Bandersnatch of G, if I return Bobilli of y, whenever you want to know the answer to Bandersnatch of G, I have a correct algorithm. Okay? Any questions about that? Okay? We're going to say, just because I'm going to use this word a lot in the next couple of weeks, that a translation of one problem into another is something that we call a reduction. Okay? I am reducing the problem of computing Bandersnatch of G to computing Bobilli of y. Okay? That's what is special about this algorithm. Okay? Any questions about that? Now, this idea of doing a translation and calling a different algorithm sounds ridiculous, right? If it's going to keep the answers exactly the same. Have we done that in here? is there any algorithm we have seen in here, or any daily problem in here which we saw, which got solved in this way? Does anyone remember? We did have such a thing, yeah? What was that? Shortest path. Right. Remember, I had a problem in here where I wanted to solve. I asked you what was the shortest path from x to y using, k hops. Right? Remember, that is a daily problem? And do you remember what I did to solve that problem? I did a translation where I took your input graph G, and if you remember the details, I made basically k copies of it. Let me try this. I made k copies of it. Let's go away. And I made the appropriate connections between nodes. As I recall, I had all my connections pointing down. Remember that? I made it a directed graph. And then I said, the shortest path from here to here was going to tell me exactly what was the shortest path using k hops to get from here to here. Right? So I did actually have an algorithm like this. Okay? And what did that algorithm work? It worked by translating the input of one problem into the input of another problem for which I knew a fast algorithm. Okay? Does everybody get that? Do people see that? It shouldn't seem so crazy for an algorithm to look like this. Okay? We've seen at least one real algorithm that looks like this. Most algorithms don't look like this, but we've seen at least one real algorithm that looks like that. Any questions? Okay? So do people understand this Bandersnatch algorithm? How it works, what it does? Okay. What does this Bandersnatch algorithm mean? I am going to claim that this Bandersnatch algorithm could mean one of two things if you have such an algorithm. Okay? And that's the second slide. What does this mean? Okay? Suppose my translation from the input G of Bandersnatch to the input Y of Bobilli. Suppose that translation took polynomial time. Maybe it took n squared time, maybe it took n cubed time. Okay, n cubed log n, I don't know what it is. But I'm going to claim that algorithm means one of two things. If the Bobilli solver runs in p prime of n time, okay, then the Bandersnatch algorithm runs in the time it takes to do the translation plus the time it takes to call the Bobilli solver, right? If I have a fast translation and a fast Bobilli solver, a fast subroutine to work on the translated data, then this gives me a fast algorithm for solving Bandersnatch. Does everybody agree with that? This is what happened on that shortest path type problem. My translation took something like n squared time, and then calling Dijkstra's algorithm on shortest path, well, you know what that is. That's something like n squared time. So n squared time plus n squared time, it gave me an algorithm that ran in n squared time. So that's one possible implication of this algorithm. But the other implication is, suppose I know absolutely, sworn in stone, that there is no fast algorithm to solve Bandersnatch. Suppose that Bandersnatch is a provably hard problem where no algorithm that runs can possibly run faster than P prime n for solving Bandersnatch. What does this algorithm imply? Let's go. If the Bandersnatch problem can't be computed fast, and my translation is fast, and Bobilli on the translated thing would give me the answer to Bandersnatch of G, then what does this mean? It means there can't possibly be a fast way of solving Bobilli, because this algorithm would give you a fast way to solve Bandersnatch if there was a fast way to solve Bobilli. Let me say that again. I'm going to go back and look at the Bandersnatch algorithm. Suppose we look at this thing. Suppose I tell you by the voice of God or Skeena or anyone else you really, really trust, okay, that there is no possible fast way to compute Bandersnatch. There is no polynomial algorithm for solving Bandersnatch that is possible. And suppose you show me this thing. This thing is an algorithm for computing Bandersnatch. Bobilli of y is always equal to Bandersnatch of g. So it's a correct algorithm for solving Bandersnatch. Suppose you show me that this translation is fast. Let's say order n cubed. What does this algorithm mean? Well, if there was a fast way of solving Bobilli, then this would give you a fast way to solve Bandersnatch, right? But is there a fast way to solve Bandersnatch? No. Why do you know there isn't a fast way to solve Bandersnatch? Because the authority of God tells you that there is no fast way to solve Bandersnatch. If there is no fast way to solve Bandersnatch, and you can show me an algorithm to solve Bandersnatch quickly, if you could solve Bobilli quickly, what does that mean? That means that there's no way that Bobilli could be solved quickly. Because if you could solve Bobilli quickly, this would be a fast algorithm. Okay? Therefore, we've just proven that Bobilli is every bit as hard a problem as Bandersnatch. That's what this algorithm would prove. Okay? Any questions about this reasoning process? Yes?
Can you go through the reasoning again?
Could I go through the what?
The reasoning again?
The missing a word.
Reasoning.
Say that one more time.
Reasoning.
Someone else say that differently.
Reasoning.
Reasoning. Yes, I will go through that. Okay? First, let's make sure we understand what this thing is. Does everybody see that this is an algorithm for solving the Bandersnatch problem? That you should be able to look at. Does everybody agree it's an algorithm for solving Bandersnatch? Does everybody agree that it is a correct algorithm for solving Bandersnatch if we did this translation in such a very careful, subtle, magic way that Bandersnatch of G is equal to Bobilli of y? Suppose this was always true, a function of how we did the translation. Then not only is this an algorithm for computing Bandersnatch, it is a correct algorithm for computing Bandersnatch. It's not a fake thing. It just, it's not like a thing people write on an exam. This is, if Bandersnatch of G is always equal to Bobilli of y, if I return the answer of Bobilli of y, I'm returning the answer of Bandersnatch of G. Okay? So if this property holds, okay, as a result of how I did that translation, then this is a correct algorithm for solving Bandersnatch. Okay? It depends on me proving that I could do this translation in a way that mobility of y is equal to Bandersnatch of g. But I did that on that shortest path problem, right? I convinced you that I could take your graph, translate it into a somewhat bigger graph, such that what you wanted to know, okay, was in fact shortest path on this new graph. In fact, how did I do that? That algorithm, let's go back. What was that called? Did I remember what I called that problem? I think I called that problem shortest path with k hops was the name of the problem. The input was what? A graph, a start vertex, an end vertex, and a k. Right? And I did a translation that took this input and produced a graph G prime with a start vertex, G prime with a start vertex in that new vertex and an end vertex in the new graph, right? And I then called Dijkstra, terrible, something bad just happened. I then called Dijkstra, sorry about this, on this, and that was going to give me the same answer as shortest path with k hops on the input. And so I returned Dijkstra, the shortest path length on G prime from X prime to Y prime, as the answer to the original problem. Okay? This is what I did in the daily problem. And it was a correct algorithm because when I did that translation, it left it so the shortest path with k hops on this was the same as the Dijkstra shortest path on this. That was why that algorithm was correct. Okay? Any questions? Okay, so here no questions. Now, if we understand what the Bandersnatch algorithm is doing, I claim there are two possible implications of this Bandersnatch algorithm. One, the first one, which is what happened in the daily problem, is that if, I think I'm going to do this here, boom, if my Bobili subroutine was fast, if my translation was fast, okay, and my Bobili routine was fast, the translation from one graph to a bigger graph, that was my translation in the old one, and that took something like n squared time. And if the Bobili routine I use within my Bandersnatch routine, if that's fast, this gives me a fast algorithm for Bandersnatch, because my algorithm is going to take translation time plus Bobili solving time. Do people see why, if Bobili is fast and the translation is fast, this is a fast algorithm? That everybody should see, right? Any questions about that so far? Yeah? Where does the n prime come from? N prime was not, okay. That's a good question. Let's take a look at, let me read this now on the second one. So, okay, so to be precise, what is this thing now saying? Recognize that if we go back to the Bobili algorithm, what is the size of the original Bandersnatch problem? Remember that was a graph? Let's say on what I was doing it was a graph. The size of this had n vertices. When I translate it into my Bobili y, does my translation have to have the same number of vertices as before? No. In fact, in that translation, I made it bigger. Okay, I made it k times bigger, right? So n prime is going to be the size of y. Okay? So there's the size of the original input, and there is the size of the translated input. And that they need not be exactly the same, right? Probably y is going to be a little bit bigger. I don't think I'm going to translate it and make it smaller. If so, you did a dumb way specifying your original problem. I'm going to make it somewhat bigger, but hopefully not too much bigger. Okay? So now what does this say? Okay? If my translation routine ran in time p of n, which is polynomial in the size of g, it produced something, a y, which was this big. Now, if Bobili runs in p prime n time, okay, that is the size of Bobili on an input of size n, right? Now, the Bobili input isn't really of size n, but it's of size translated, runs in translated size, right? That's why I've got p prime, it's Bobili time on the size of what I'm giving Bobili. That's why I've got p prime and n prime there. Okay? Any questions? Okay? So, if Bobili solving is fast and translation is fast, this gives me a fast algorithm. But for the purposes of the rest of the semester, I'm going to be interested in this implication. Suppose I know that there is no fast way, okay, for you to, there's no fast way for you to solve the Bandersnatch problem. It violates all the laws of physics to solve the Bandersnatch problem quickly. Okay? It violates the mission of God or whatever else. There's absolutely no way you can possibly solve Bandersnatch quickly. Does that mean that this algorithm can't exist? No, certainly it can exist. Okay? Maybe Bandersnatch takes let's say that the fastest Bandersnatch algorithm ran in, let's say, n factorial time. Okay? Let's say I could prove that. What does that mean? Does that mean that there can't be a Bandersnatch algorithm like this? No. Okay? Does that mean that you couldn't find a proof that Bobili of y is always equal to Bandersnatch of g? Certainly it's possible to do that, right? And is it possible that you did that translation so the translation took order n squared time? No reason why not. But suppose you do. What does this mean? If you have a fast Bobili solver, this would give you a fast Bandersnatch solver. Okay? Let's say you could solve Bobili in order n to the 100th. Suppose you gave me a Bobili solver that ran in order n to the 100th. Maybe the size of your translator took an instance of size n into a size n squared. The Bobili solver would give you an answer in something like n squared to the 100th, which I think is n to the 200th. Could that be possible? No, because if it could, this would give you an order n to the 200th algorithm. I told you that there was no algorithm that was better than n factorial. Okay? Therefore, you could not have an n to the 200 algorithm for solving mobility. Okay? You can't have an n to the 5,000 algorithm for solving mobility. The fastest possible mobility solver would be what? Something that ran in n factorial minus n squared time. That is the fastest, actually, that is the fastest algorithm that you could come up with for solving mobility. And you're proving that by the existence of this Bandersnatch algorithm. Okay? That is the reasoning that we're trying to do here. Okay? Any questions about this reasoning? Does everybody see that an algorithm like this, for solving Bandersnatch quickly, if you can solve mobility quickly, and an argument that says, no, 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 there's no way to solve Bandersnatch quickly. The implication of those two is there is no way to solve mobility quickly. Any questions about that reasoning? Yes? Well, okay, how did you know that, there was no fast way to solve Bandersnatch? Well, suppose the voice of God told you this. Or Skinner, if you trusted Skinner as much. Right? But if you know that there is no fast way to solve Bandersnatch, this gives you no fast way to solve mobility. Okay? As an implication from that. Any questions? Okay, we'll get into a little bit. It's a little bit more than just Skinner says so. Okay, as we'll see. But for now, Skinner says so is a good enough explanation if you trust Skinner, right? Any questions? Okay. Any questions about this reasoning? If you understand this reasoning, you will understand the next 2 weeks' worth of classes. And if you don't, well, you're going to get another crack next class, and the class after, and the class after. Any questions? Okay, good. Now, I once, again, I have a little Twitter account, okay? I don't tweet that much. This is the best tweet I ever made, okay? And if you can understand how profound this tweet is, okay, you will go a long way here. An NP-Completeness proof ensures that a dumb algorithm that's slow isn't a slow algorithm that's dumb. Okay? What does this mean? Under what condition is a slow algorithm dumb? Yeah? If there's a fast algorithm saying, hey, I got a slow algorithm, what do I look like? I look dumb, right? Now, what is a dumb algorithm that is slow? Have any of you developed dumb algorithms that are slow? Okay. Yeah? Backtracking is a dumb algorithm that's slow. Hey, I'm going through all the possibilities one by one by one, and I'm going to take the best one of them. Is that a dumb algorithm? It's a dumb algorithm. Now, you may say it's not a stupid algorithm. A stupid algorithm goes through all of them once, okay? Hopefully with backtracking you were a little bit more clever. But notice all your backtracking programs hit a wall at some point, right? It was faster than going through all the solutions one by one, but it still went through an exponential number of solutions before it was done. Okay? That's why it hit a wall. Okay? An NP-Completeness proof is telling you when basically backtracking is about as good as you can hope to do, right? Because if I can prove that there's no fast algorithm, having a slow algorithm is nothing to be ashamed of. But if there is a fast algorithm that you haven't figured out, that is dumb. Okay? Any questions about this? Okay? Fair enough. Let me go through now. Any questions at this point? We're going to get a little more into some lower level details now. That's kind of important for thinking about this stuff. Okay, but any questions about the big picture here? Okay, so in this section, when we talk about NP-Completeness, we're going to be talking about what algorithm problems are and algorithm problem instances are on a more, let's say, technical level than we did before. I did mention these words at the beginning of the semester. An algorithm problem, remember, is a general question. Okay? It specifies the input parameters, and it specifies what the conditions of a satisfactory solution is. Okay? So when we talk about the traveling salesman, what is the specification of problem input? It says, given the following input, which has to be a weighted graph, what do I want to do? Find me the tour, which has what property? It minimizes the sum, it visits all the vertices, yet sums, yet sums up to the smallest amount. Okay? So did everybody get the idea of what what a problem is? A problem is a specification of what allowable inputs are and what allowable outputs are. Okay? Any questions? When we go back to our Bandersnatch thing, what do I got? Boom. What here is an algorithm problem? What on this slide is the name of an algorithm problem? Yeah? Bandersnatch and Bobilli are both algorithm problems. They have to be specified. They have specified inputs, and they have specified what the output is, given the input, what the right output is. Okay? Does everybody see? Those are the algorithm problems. Okay? There are also things that are called instances. I'm going to talk about instances from time to time. What is an instance? An instance is kind of the input to a problem. Okay? So that when you say what is the input to the instance, an instance of a TSP, that could be the instant input to a particular TSP problem. You could specify it as a graph. You could weighted graph. Or maybe you could specify it as a set of for every possible input pair, what's the cost of it? I could specify it by an adjacency list. I could specify it by an adjacency matrix. Does everybody see that there are different types of possible inputs that would represent it? Okay? But the instance of a problem is the input parameters for a particular problem. It's a specific, execution, if you wish, or specific input to a specific problem. Any questions? So when we go back to our Bandersnatch thing, what are the instances? Get back to this here Bandersnatch thing. What are the instances here? Yeah? Not Bandersnatch of G, I'm going to just say G. Okay? And is there any other instance here? Yeah? Y. Those are two instances, right? We're going to be translating, our translator here is taking an instance of a problem, an instance of problem P1, and translating it to an instance of problem P2, right? So what we're needing to do, our translating here, is a general purpose reformatting thing that reads the input to Bandersnatch, which whatever form it's supposed to be specified in, and translate it into a well-formed instance of Y, an instance for mobility. Any questions about it? So understand when I talk about the difference between problems and instances. Problems are high-order things we want to prove things about. Instances are things you might want to execute an algorithm on. Okay? Any questions? Okay. Got to keep that straight. What else is important to know about? Actually, sorry, hold on. It's doing something weird right now. A problem where the answers are only yes or no is something we're going to call a decision problem. Remember, an algorithm problem is a big problem thing. The input is some kind of instance. The output, it's going to produce an answer. A problem is a decision problem if the only possible answers are yes and no. Is there any problem we've discussed this semester where the only possible answers are yes or no? I'm not completely, yeah, what? String shuffling was a decision problem, right? The input was I was giving you a string X, a string Y, and a string Z, and I basically asked you, can you shuffle X and Y to get Z? Right? And the answer for any X, Y, or Z was either true or false. Okay? So some interesting problems happen to be yes-no problems. Okay? More importantly, almost any interesting problem can be expressed as a decision problem that captures the essence of why it is interesting. Okay? So yes-no problems seem like they're simpler than other problems, right? If I gave you a decision problem on the exam, and I gave you an input instance, and I said, tell me what the answer is on this. Does everybody agree that on a decision problem, random guessing should give you a 50% chance of getting it right, right? Normally, if I say, give me a traveling salesman cost for this, random guessing probably isn't going to do you much good, right? So it might seem that decision problems are easier than regular problems. But that's not really true, actually. Almost any, optimization problem can be expressed by a yes-no version that kind of captures how hard the original problem is. Okay? Suppose I think about the following yes-no question. Given a graph, a weighted graph, and an integer k, does there exist a traveling salesman tour of cost k or less? Does everybody see that this is a yes or no problem? Okay. Given a graph and a bound, is there a tour of cost less than k? Is this a yes-no question? The answer is yes, obviously. Either the best tour is less than cost k, or it's not less than cost k. If I gave you a fast algorithm for solving this yes-no question, could you give me a fast algorithm to find the traveling salesman, the cost of the optimal traveling salesman tour? How would you use this algorithm? If I gave you a fast algorithm for this yes-no question, could you tell me the cost of the optimal salesman tour, traveling salesman tour for a given graph quickly? How would you do it? Somebody. Okay? Yeah?
We can start at k, and then if it's less than k, we can go lower and lower until we find.
You're saying that I can do something, maybe even something like binary search. If I knew an upper bound and a lower bound on the cost. Do you see how I could run this thing log times and get this optimal cost, right? Suppose all the edge weights are positive in the graph. What's a lower bound on the cost of the traveling salesman tour? Can anyone give me a number that's strictly, let's say they're integers also. Can anyone give me a lower bound on the cost of the optimal TSP tour for this graph? Lower means a number that is below it, yeah? The number of points? Well, I guess if every edge has to have weight at least 1, then it is. I'm going to be even sloppier. Do people agree that 0 is a lower bound? Can anyone give me an upper bound on the size of the optimal tour? Yeah? Does anybody agree that the sum of all the edges over all edges I, comma j, the optimal TSP tour is going to involve n of these edges, right? Does everybody agree we've got a lower bound? We've got an upper bound? If I start with k equals this plus this divided by 2, that's the midpoint, right? If you tell me there is an optimal, I ask you one question. If the answer is true, then the optimal tour is somewhere between here and here. If the answer is false, the optimal thing is here and here, right? By calling it this thing. If it was true, I get the answer is no. I check here, the answer is yes. The answer here, I get no. Okay, the answer is somewhere between here and here. If I could solve this decision problem quickly. Does everybody see that I could solve the real hard TSP problem that you want quickly? So yes-no questions are powerful, right? And from now on, I'm only going to talk about yes-no questions, decision questions. Because I'm going to tell you for any problem you really care about, I'm going to give a meta answer that there is almost certainly a yes-no version of it that will, capture why it is easy or hard. What makes that problem interesting? Any questions? Why am I going to be interested in yes-no questions? Let's go back to this Bandersnatch thing again. Why am I going to be interested in decision problems? Problems that can only be yes-no questions. Can anyone look at this and tell me why? If I'm going to do Bandersnatch algorithm type of things here, decision problems are good things? Well, what is the heart of the thing that I'm trying to do here? I have to come up with this translation routine, which looks pretty hard, and I've got to make it so that Bandersnatch of G is always equal to mobility of Y, right? That's the heart of what I'm doing. Is this going to be easier to do for decision problems? Well, now there's only two possible answers here. This is a true or a false, and this is a true or a false. By thinking about decision problems, all I have to do is that whenever mobility of Y is true, I want Bandersnatch of G to be true. Okay? Do you see how it's easier to kind of think about the two problems being the same when they're decision problems? How many people kind of see that? Okay? So we're only going to think about decision problems from now on because it makes our work easier. Okay? But I want you to be convinced that I'm not hiding anything here. The traveling salesman problem has a decision problem that really captures the guts of why traveling salesman is hard. Did we have any other problem here that was hard? You know, it's not very, what would be the way we would make an edit, turn the edit decision distance problem? What would be the decision version of the edit distance problem? How do we make that a yes-no question that you can probably only answer if you know how to do the real edit distance? What would be a decision version of the edit? Yeah? Is the edit distance less than or equal to some target? If you're good at answering that correctly, you probably know how to do the full optimization problem. Okay? Any questions? So from now on, we're living in a world of yes-no problems. Okay? And we're not doing this to cheat. We're doing this to make our lives easier. But on the other hand, this still doesn't really change the generality of what we're doing here. Any questions about that? Okay? Any questions? Again, a reduction, okay, is the idea of transforming one algorithm problem A to another algorithm problem B, is saying that if you know how to solve B, okay, you can solve A. Okay? Can anyone give me a quick algorithm for finding the mode, a fast algorithm for finding the mode of a set of integers? I give you an array of integers. I want to know the most frequent integer. What is the way that you would do that? Does anyone remember? We did that early on in the semester. How would you find the mode of a set of integers? Okay, what'd you do?
I sort it and then go through.
You sort it and then you sweep it, right? What's the running time of this? Well, sweeping it takes order n. What's the running time of sorting? Well, I've reduced this to sorting. Depending if some smart guy finds a faster way to sort, they've made my algorithm faster, right? The hard part of my thing is now reduced to another problem. Any questions? That's the way I like to think about this. Okay, any questions? So fairly often we're used to the idea of transforming one problem to another. It's a good way to think about things. Okay? There's a joke about computer scientists and engineers that involve reduction. Okay? And if you laugh, it means you understand the concept. If you look at it like it's stupid, you need to keep thinking. Okay? An engineer and a computer scientist are sitting around the kitchen, okay? And the engineer says, I want some tea. The engineer gets up, grabs the tea kettle from the shelf, okay, fills it with water, okay, takes that, moves it to fills it with a lot of water, moves it to the stove, turns on the stove, okay, waits a while, the tea kettle boils. He then takes the water and pours it in a teacup and puts it in a tea bag, okay? The computer scientist is watching this with great interest, of course, okay? They sit down for a while. The engineer, of course, puts the tea kettle afterward, puts it back on the stove. The computer scientist says, I want some tea. So what does the computer scientist do? Goes to the stove, takes the tea kettle with a lot of hot water in it, pours the water down the drain, dries off the tea kettle, puts it back on the shelf, and then sits down. Why is it? I have now reduced it to a solved problem. Okay? Does everybody see how he solved the problem? He reduced it to something that he knew how to do from watching the engineer. And that is the idea of a reduction. Any questions? Okay, I can tell how nobody found that funny, so that may be a sign that we still have more to teach in here. But any questions about that idea? Reductions are going to be what we're going to be thinking about here, transforming one problem into another. Any questions? Okay. I'm going to go on because we have some time. I'd like to go on to the start of the next lecture and start to make this more complete by starting and telling you what is the mother of all NP-complete problems, okay? You guys were telling me, oh, if I'm going to be doing this, I know I need Bandersnatch has to be hard. How do I know what's a hard problem for Bandersnatch? The mother of all hard problems is a problem called satisfiability. And satisfiability is going to be a yes-no problem. It's going to be a logic problem. Okay? The input of it is a set of variables, Boolean variables if you want. Boolean, remember, means true or false. Variables, and a set of logic clauses over those variables. And it asks, is there a way to make that expression true? Okay? So let's look at a logic expression. One logic expression that we're going to look at here is, trouble. V1 or not V2 and not V1 or V2. People see that as a logic variable? V1 or not V2 and V1 or not V1 or V2. Is there a way to make this logic variable, this logic statement true? Okay? See, I've got this thing. How do I make this logic statement true? Can anyone give me a way to make this logic statement true? Yeah? You're saying V1 equals true, and what? V2 is equal to true. That would be true or not true. What is not true? False, right? And what is not true? That's false. Or V2 is true. Does everybody see that true or false is true? False or true is true. True and true is true. Right? By setting V1 to V2, okay? V1 equal to true and V2 equal to true. Does everybody see that that makes this particular logic expression true? Is there any other way to make this logic expression true? Yeah? What if I make them both false? Then this is going to be what? False or not false, which is true. This is going to be not false, which is true, or false. True or false is true. False or true is true. True and true is true. Right? So this particular expression has two different ways of making it true. Does everybody see that? Okay. Now, just to make sure you understand my notation, I am going to write that logic expression like this. What is the way to read it? Okay. The clauses that I'm going to be giving you are the commas mean or, if they're within the bracket, and they are an and between that. Right? So I'm going to want to take this. That becomes an and. This becomes an or and an or. Okay? So what is the Boolean satisfiability problem? I am going to be giving you sets of, sets of Boolean literals, either the Boolean variable or the negation of it. And I'm going to say, I need you to find a way to set every variable to be true or false, so that each one of my subsets, which I'm going to call a clause, has at least one true thing in it. That's what satisfiability is. Is there a way to set the thing so that each subset here has a true literal in it? You guys showed me that there's two different ways to satisfy this problem. Any questions about that? Okay. I like to think of it in this format. You might be needing to translate it in your head into that logic thing. Basically, a satisfiability problem is the anding of a lot of or clauses. Okay? Any questions? And the question is there a way to make it true? That is the heart of what satisfiability is. Okay? Let's look at another example. Sorry if it's here kind of painful. What about this Boolean formula? Is there a way to satisfy this? This is over two variables, V1 and V2. Is there a way to satisfy this thing? Okay. Is there an assignment of true and false to V1 and V2 to make this true? See, some people say the thing is saying no. That may be because they're expecting my setup. But what would I know? If I've got a clause here with only one literal in it, what does this clause tell me about V1 if I am going to satisfy this? Yeah? What? V1 has to be equal to false. If V1 is not equal to false, I lose the game at the beginning. Does everybody see that? Well, here, if V1 is false, false or something is false, right? What does that tell me about V2? V2 had better also be false. If V2 is not false, I lose the game, right? But notice that if because of this last clause, if V1 and V2 are both false, I do lose the game. Although no matter how hard you try and you try and you try, you can't get no satisfaction for this expression. Okay? Any questions about that? Does everybody see that this is now an algorithm problem? Satisfiability is an algorithm problem. I am giving you as input a description of the logic expression, and you have to find what makes it true and what, are there variable assignments that will make it true. Okay? Any questions about that? Can anybody give me a correct algorithm for solving satisfiability? Yeah?
Go through every variation of truth for the variables and test it.
You say go over every possible truth assignment and check it, right? If I have n variables, and let's say m clauses, okay, what is the running time of your algorithm?
2 to the n times n.
It's going to be 2 to the n, because you're going to try every possible pattern of trues and falses. Right? Does everybody see that? And for each one, you got to check it. Right? And how much time does it take to check it? Well, it could be something like, I'm going to say an upper bound would be m times n. Each one of these m clauses might have n different things in it. Right? So I'm going to say this is an upper bound. This is the running time of an algorithm to solve satisfiability. Does everybody agree with that? It should be obvious that the brute force search algorithm is correct. It should be obvious that the brute force algorithm is going to take time that is exponential in n. Order 2 to the n. Okay? But maybe there would be a faster way of doing it, right? Just because there's a slow algorithm for doing something, does that mean that there's not a faster way to do it? It could be there's a faster way to do it. Maybe. Except, satisfiability is a hard problem. We know that satisfiability is a hard problem. Okay? Why do we know it? Well, there are a couple of reasons. One is because the whole algorithms community has built the theory of NP-Completeness on top of satisfiability being a hard problem. Satisfiability, every algorithms person in the world agrees nobody knows how to solve satisfiability. Why do we know this? What if you guys go home and come up with a fast algorithm for satisfiability tonight? What are you going to do? You're going to come to me and say, hey, Professor Skeena, can I get extra credit if I have a fast algorithm for solving satisfiability? And I'll say, sure. And I'll then look at your algorithm, and what am I going to do? I'm going to call the New York Times. It would be the front page news in the New York Times tomorrow if somebody came up with a fast algorithm for satisfiability. Every algorithm person in the world knows that satisfiability is the target. Okay? You find a fast algorithm for satisfiability, you are world famous. How do I know there is no algorithm out there for solving satisfiability? Because if someone had it, they would want to be famous, and it would get out there. Okay? Any questions? Okay, so that's one reason why I believe satisfiability is hard. Turns out that there are other reasons why satisfiability is hard, okay, that are harder to explain or to convince people of. But there is one thing that I could show you is if you came up with a fast algorithm for satisfiability, using some other magic that we're not really going to talk about in here, you could have a fast algorithm for any problem we have talked about this semester. Okay? If you find a fast algorithm for satisfiability, you're going to get a fast algorithm for traveling salesman. You're going to get a fast algorithm for clique. You're going to get a fast algorithm for independent set. You're going to get a fast algorithm for thousands of problems people care about. So it's not only the stakes that, well, I get to be famous if I find a fast satisfiability thing. I change the world because all problems now, for a certain value of all, have fast algorithms if you can get satisfiability fast. Okay? And that seems like that's now an even stronger guarantee than Skinner not knowing how to do it, right? Anything people don't know how to do would suddenly be fast. And there are other complexity theoretic implications that are weird. The world would be collapse in weird ways if you found a fast algorithm for satisfiability. Do I mind you working this weekend on it? Okay, I think it's fine if you want to go think about it. Okay? But for many reasons, we believe satisfiability is a hard problem. Because satisfiability is a hard problem, what does that mean? Where does satisfiability sit in our Bobilly-Bandersnatch continuum? What is the role that satisfiability is going to play? Someone with a louder voice? What is satisfiability going to be for us? Yeah? Satisfiability is not going to be Bobilly. Satisfiability for us is going to be Bandersnatch. What is the situation? Satisfiability is known, and by the way, this is a common mistake, so don't feel bad. Okay? Satisfiability is a hard problem. There is no fast way to solve it. But what happens if I give you a way to translate the input to satisfiability into the input of the input y for some problem called Bobilly, such that Bobilly of y was always sat of g. Do you see that if Bobilly of y is the same answer of sat of g, okay, then this is a correct set solver. If that is true, what do I know? If the translation takes polynomial time and there is no possible way of solving sat faster than order 2 to the n, then what does this tell us about Bobilly? Tells us that there is no fast way to solve Bobilly. Okay? So the important thing is that satisfiability is going to give us our Bandersnatch. Okay? Satisfiability is the provably hard mother of all hard problems. Okay? Any questions about that? Yes?